talking about fired heaters, talking about the importance of tube metal temperature, the salient features of inclined firing. We will present a case study, and then we will have a question and answer session at the end of the presentation. Let me take this opportunity to explain how we developed inclined firing technology. It goes back to 2005. We had a client in Texas. They had a crude and vacuum heater in one of their crude units. They were looking to increase the capacity of their heaters by 25%. They were working with an EPC company which was involved in the project, and they looked at the heaters and they said these heaters have already been revamped once. The capacity has already been increased. So this heater cannot be revamped any further. And I think it will be best to put new heaters for the extra heat duty. So the project and the client agreed, and they started working on new heaters. But within a couple of months, they ran into a problem, and the problem was there was no space available to install new heaters in that unit. So the client came to us and said, is there a way to increase the capacity of these heaters by another 25%? We said we need to study it, and we will find out if there is any possibility of increasing the capacity. So we looked at the heater, carried out engineering study, looked at the operating conditions, and then developed proposed revamp scenarios. And then we came back to them with two technologies at the same time. We said your heater design is very, very tight. We need to put the burners at an angle. That will allow us to increase the firing rate even further. And the second thing we told them was that we want to inject about 30% flue gas in the radiant section. And by injecting flue gas in the radiant section, what we are doing is we are transferring the heat from the radiant to the convection. It is very difficult to add surface in the radiant section, but it is very easy to add surface in the convection section. So we said when we can shift whatever extra duty you need to the convection section, and we can increase the capacity by 25%. The client liked our idea. We went into phase 2. We did a fair amount of engineering, but suddenly the project got cancelled because the project cost got too high and the crude prices crashed, so the project was cancelled. But we were excited about these two developments. We decided to move ahead and install it in other heaters. So this is how we developed this simple inclined firing technology. I want to talk to you a little bit about how heat is transferred to fluids in fired heaters. Very, very simple. We have a sketch here showing the radiant section. We have a refractory lined wall. Then we are showing tubes, and we are showing a burner flame. So in heaters, you will see that there are two modes of radiative heat transfer. There is a direct mode of radiation heat transfer, which is radiating to the front half of the tube, and that is the predominant mode. And then we have the re-radiation, which is the radiation coming back from the refractory to the back side of the tube, and that is the re-radiation. And that also contributes a significant portion of the radiation. So these are the two radiant mechanisms, and mostly it is the hot flue gases, the carbon dioxide and water vapors, and the hot temperature is what are the gases which are doing the radiation. You know, the flame never comes into the picture. So the second mode is the convective heat transfer, and about 15% of the heat in the radiant section is transferred by convective movement of hot flue gases around the tubes. And once the heat is transferred to the tube from radiation and convection, now the task is to transfer the heat from the outside of the tube to the inside of the tube. And this is where things get a little complicated, and that's what we want to talk about today. If everything is good, the heat will be transferred from the outside of the tubes to the inside of the tube. But there are two things which can happen. And those two things are either you can have a scale on the outside, or you can have coke layer on the inside of the tube. And either of the two things will start impeding on the heat transfer because they are not good conductors of heat and they will cause problems. So what we find is it's mostly the flame impingement or hot flue gases leading to formation of scale or formation of coke on the inside. But both the things are not good. And once the heat is transferred to the inside of the tube, then it is the film, the thin fluid film, which takes the heat from the metal wall or the coke and then transfer it to the bulk of the fluid. And that is the convection mode, which is transferred in. So basically, if you see, even though we call it the radiant section, all three modes of heat transfer are there, which are taking place: radiation, convection, and conduction. And in steady state, everything has to work this correctly. I'm not trying to scare you with the equations, but the basic equation we are going to be talking today was developed by Lobo and Evans, two great engineers, back in 1939. That is how far we go, and they are still holding good. Every heater company uses the same equations. And here, I want to draw your attention to only two parameters. One is TG over here, if you see, and TT. TG is the absolute temperature of the flue gas, and TT is the absolute temperature of the tube, or the tube metal temperature. And the first component is radiation component, which is predominant component, and it's nothing but Stephen-Boltzmann equation. And the second component is the convection component, which is 15%. So here we want to tell you that to transfer the heat, we are using fuel gas and burning it with combustion air. And when the combustion takes place, the temperature produced, the flame temperature produced, is in excess of 3000 degrees. And if we are using preheated air, it will be even hotter. So the power of flame is immense, and it is best to keep the high temperature flue gases away from the tubes. No material can withstand these temperatures. So in nutshell, simple theory is if you have flame touching the tube, you can call it a problem or disaster. And our basic rule is keep the flames away from the tubes as much as possible. The second parameter we are talking over here is the tube metal temperature. And this is what we are trying to control. So tube metal temperature is the external temperature of the tubes in the radiant section. It varies in the radiant section. In order to have the best heat transfer possible, you want to keep the tube metal temperature as low as possible. So the lowest the tube metal temperature, more better will be the heat, And since we are having coking service or hydrocarbon fluids inside the tube, we have clean tubes at the start of the run, and as slowly the coke forms, the tube metal temperature starts going up. And tube metal temperature, as I will explain to you in a minute, is nothing but a sum of bulk fluid temperature, temperature rise across the film, coke, and metal. I am not talking about the scale. And the thumb rule is the clean tube metal temperature should be bulk fluid temperature plus 100 degrees. That's how low the clean tube metal temperature can be if everything is right. So the tube metal temperature calculations basically talks about three components, as I said. Temperature rise across the film, temperature rise across the coke layer, and temperature rise across the metal layer. And then you add all these temperature rise to the bulk fluid temperature, and you will get your tube metal temperature. The sketch we are showing you here shows you a TMT rise, and you can see that most of the temperature rise is taking place across the coke layer. The temperature rise across the metal and the temperature rise across the film is very, very low. For those of you who are interested in calculating, I'm just giving you the formulas. I just want to show you how the tube metal temperature calculations take place. Very, very simple. The first term in all the three equations is nothing but the flux, Q by A0. So you can add, you can either use average heat flux or you can use maximum heat flux, depending on what you want to calculate. You want to calculate the average tube metal temperature, or you want to calculate the maximum tube metal temperature. The maximum heat flux is typically 1.8 times the average heat flux for single fire heaters. So, and the last term in all the three equations is nothing but the diameter correction. I mean, you can even neglect it if you just want to do an approximate, So the film temperature is dependent on the heat transfer coefficient. The coke layer is dependent on the thickness of coke and the thermal conductivity of the coke. And the metal temperature rise is dependent on the metal wall thickness and the thermal conductivity of the metal. All these equations are available in API 530 standard. So they are very well established equations. So why do we experience high tube metal temperatures? And our analysis says most of the high tube metal temperatures and hotspots are caused by flame impingement. It is also a result of overfiring, as it could lead to large flames. Flame impingement may not be easily visible, and it could be, these hotspots could be due to high flue gas temperatures in the vicinity of tubes. Tube skin thermocouples are very good indicators of high tube metal temperatures, but they only provide you with a point measurement. Infrared surveys have become a lot more common, and they can provide a complete picture of the radiant section tubes. There are two major reasons for high tube metal temperature. You can either have scales on the outside that could be causing problems, or coke inside the tube that could be leading to high tube metal temperature. Metal oxides are not good conductor of heat and can lead to an increase in metal temperature of anywhere between 50 to 100 degrees Fahrenheit. Similarly, the coke formation on inside the tubes can lead to a temperature rise anywhere between 50 to 200 degrees. So if you have a crude heater operating with a 650 degree outlet temperature and your tube metal temperature is 1050, you can start thinking about that extra 300 degree increase is coming either from scale or from coke. That's basically what is happening. So coke buildup or external scales, that could be the two reasons. Let us look at the coke. If you see the metals have thermal conductivity anywhere between 200 to 300 BTUs per inch. And coke, depending on whether it is fluffy coke or whether it is hard dense coke, the thermal conductivity can vary between 1 to 30. We typically use 15 in refinery applications. So the coke has 10 times lower thermal conductivity or 10 times the insulation value. So If the metal temperature rises 25 degrees, the temperature rise across the same thickness of coke will be 10 times or 250 degrees. The thumb rule is 1/8 of an inch of a coke adds up to 100 degrees of tube metal temperature rise. This is a picture of coker heater, and if you look closely, you can see the scales on the tubes. That's how bad the situation was. This is the double-fired heater. I don't have to tell you what happens when coking starts, but coking of tubes will lead to several problems in fired heaters. Tube metal temperature starts going up. Fluid side pressure drop also starts increasing. Firebox temperature goes up. To maintain the same heat transfer, the firing rate goes up, the efficiency comes down, and ultimately the charge rate starts limiting. And finally, you have to shut down the heater and either decoke it or peg it to clean the tube and then start all over again. And that's a very expensive shutdown if you have to do it. So here we are showing you a radiant tube metal temperature profile. And even though the model we use for our calculations is based on continuous stirred tank reactor, that means the flue gas temperature across the whole heater is uniform. There is only one temperature, but that does not happen actually in real life. So you can see in a case of a vertical cylindrical heater, you can see the hotspots over here. You can see these hotspots, and the temperature is almost like 1130, 1150 degrees, so you can see this hotspots. Similarly, this is another depiction of radiant heat flux in a vertical cylindrical heater. We are trying for uniform heat transfer and uniform heat flux in all the radiant section, but the reality is much different. The presence of ultra low NOx burners and long flames have created zones of high and low temperatures. The industry has also moved to long, narrow boxes to save money, and that creates a temperature gradient in the firebox. And this gives us a very different flux profile. Our experience is that flames remain straight for only 10 to 15 feet. They are just gas jet, and afterward they start losing shapes. The flames are drifted towards the tubes, causing high tube metal temperature. And in this slide, you will see the flux variation actually, and you will see the flux variation in the whole length of the tube. The top 1/3 is only 7,000, the middle 1/3 is 15,000, and the bottom 1/3 is 22,000, almost 3 times what is happening on the top, and the average is around 13,500. So you could see how much flux variation we can have. And you can also see the maximum heat flux going almost like 37,000. And this will definitely lead to coking and high tube metal temperatures in fired heaters. So I did some research, and I looked at API 560, I looked at API 535, and I looked at what type of solutions are available if you have high tube metal temperatures. And I found that there is no permanent solution available. They are all telling about change the burner tip or check the burner tip angle, check the burner tip location, or if your tip is plugged, So poor mixing of fuel and air, flue gas recirculation pattern. So I could not find any real fix to solve the high tube metal temperatures in fired heaters. So these are all temporary fixes, and our experience is once you start having high tube metal temperatures, then it is not a question of when, but how. It's not a question of what needs to be done, but when will you have a shutdown, and how long can you avoid it?